All right, so guys, we're ready to look at a few examples now of using this first derivative test in identifying intervals of increase and decrease, as well as relative maxes and mins. So our first example here, we just have a basic polynomial. But as I start any of these examples and you look into the homework, kind of knowing where some common mistakes have happened in the past and hopefully trying to avoid them in the future, the absolute best thing you can do anytime you're considering analyzing a function, as we are, is to first establish the domain. I know that might not say that every time, but if you establish the domain first, you'll save yourself a lot of careless mistakes down the road. So being a polynomial, our domain is negative infinity to positive infinity, which is, again, good to know. Now, to find these critical values, this is where we're going to take the derivative, which is going to be 3x squared minus 12, and set it equal to 0. So when we solve this, we get x equals plus or minus 2. So remember, by taking the slope and setting it equal to 0, these x's are the places on our original graph where we have a slope of 0 on our tangent line. And so we're trying now to decide, is it going to be a change from increase to decrease or decrease to increase, or what's exactly going on? So these right here, these would be our critical values, x equals plus or minus 2. So then what I would do now is I would come down and I would put these on a number line. Now this number line I'm going to label as f prime. This is the first derivative test. There will also be a second derivative test to follow, and so labeling the number lines is going to be very important to keep things organized. So I'm going to come over here and make a number line where I have negative infinity, positive infinity, and I'm going to put my critical values on the number line. So now I'm going to take numbers within each of these intervals. Maybe I'll take a negative 3, maybe I'll take a 0, maybe I'll take a positive 3. They just have to be numbers in that interval. And then I'm going to take those red numbers and I'm going to go back into the first derivative. Okay, so I'm coming back into this guy right here. So when I take a negative 3 and I plug it in here, when I simplify that, that's going to actually give me a positive quantity. When I take a 0 and I plug it in here, that's going to give me a negative quantity. And when I take that last number 3 and I plug it in here, that's going to give me a first derivative of a positive number. Okay? So again, I'm just taking these numbers and I'm plugging them into the first derivative right here to see if what I'm coming up with is going to be a positive or negative slope. Things that have positive slopes mean we are increasing. Things that have negative slopes mean we are decreasing. So from this particular example, it looks like we would be increasing from negative infinity to negative 2, union 2 to positive infinity. It also looks like we would be decreasing from negative 2 to 2. So by understanding now that the graph is going to be increasing and then changing to decreasing, increasing, changing to decreasing at x equals negative 2, that also means we are going to have a relative max at negative 2 and then f of negative 2. So the notation that I'm using here is something that I will look for in the written work. My math lab will obviously ask for different things in different ways, but regardless, it's the same thing. To find our actual maximum value at negative 2, to find my y value, I would take the negative 2 and I would plug it into the function. So f of negative 2 would give us this y value. Okay, so we've got an f, we've got an f prime. We're being very clear to distinguish between what is what. So these red numbers went into the derivative, that's why I've labeled it. But to find the actual maximum value, to find the actual highest y value, I take my negative 2 and I plug it into the original function f. So then we also can see that we are changing from decreasing to increasing. If we're changing from decreasing to increasing, that's going to be a minimum value, so a relative minimum at 2 f of 2. Okay, so Again, the first derivative test has given us intervals of increase and decrease and our relative extrema on the graph. I would encourage you to pause the video, take a second, graph this thing right here on Desmos, and confirm, in fact, that we do have our intervals of increase and decrease and our relative extrema correct as well. Okay, so for our next example, we've got our function here, x over x plus 1. And normally in class I would say, okay, what's the first thing we do? And many times people say find the first derivative. But remember, the first thing we're going to do is not find the first derivative, but instead identify the domain. So we can see our domain here would be everything except -1, right? We have a vertical asymptote at -1. So now I'm fine with going ahead and finding that first derivative, which when you find it and you simplify it, this is what you end up with, okay? So now, when we look at this and we set it equal to 0, we have a little bit of an unusual situation, right? We can't actually solve this for x. There's no x's that are going to create or make our derivative equal to 0. So what does that mean? Well, that means by taking the derivative, setting it equal to 0, it does not imply there aren't any critical values. It just says there aren't going to be any places on the graph where the slope of the tangent line is going to be 0. So we have to consider other possibilities if they are even there. And in this case, they are. And we know that from our domain. We have a domain restriction. X cannot be -1. And so we need to put that on our first derivative number line to, again, better understand what is happening with our graph being increasing and decreasing, and are there any extrema. So if I put this -1 on here, and I'm also a big fan, guys, -1 is not on the graph, okay? This is a vertical asymptote, so I'm a big fan of marking that. Anything unusual, I usually mark to make sure that I don't unintentionally include it maybe where I shouldn't. So I'm going to mark that vertical asymptote. I'm going to come over here and I'm going to pick some numbers on either side, maybe a -2 and a 0. And then you can take those numbers and you can plug them in up here. Now in this particular case, we really don't have to work too hard because my numerator of the derivative is always positive. My denominator is always positive, so you really don't even have to plug the numbers in if you don't want to. You know these are going to be positive. Okay? So what does that mean about our interval of increase and decrease? Well, we are increasing because of the pluses, and so increasing in this case, again, it's so important, guys, to understand why this is here. This is not a point on the graph. If you had overlooked this and went ahead and just done this and said, okay, this is always positive, so we're going to be increasing from -infinity to positive infinity, that would be incorrect because -1 is not actually a point on the graph or a place on the graph even. So our increasing interval would need to be -infinity to -1 union -1 to positive infinity. So had we not had this discussion, we might have missed this union right here and had just assumed it increased all the way through when in fact it actually doesn't. So again, these critical values are going to come from some different places from time to time. We just got to be on the lookout for them. Now, again, in this case too, you're not going to have any relative maxes or mins because you don't have any changeovers from increasing to decreasing or vice versa. So in this particular problem, the only information we're gathering out of the first derivative test is the interval of increase right here. Okay, so in this example, we'll start the same way, our domain, and this function looks a little messier, but it's really not. This is x squared and then cube rooted. So being the cube root that it is, the domain is going to be everything. We'll go ahead now, take the first derivative and simplify. And once I have that, as always, I would set it equal to 0. Now, much like the last example, by setting it equal to 0, we really don't get anywhere. You can't solve this thing for x. But, as we also saw in the last example, that doesn't mean we don't necessarily have any critical values. Now, our domain is everything, but we still have a critical value at x equals 0. Knowing the domain is everything, but looking at your first derivative and seeing that x can't be 0 in your first derivative, because you can't have a 0 in your denominator, this x equals 0 is your non-differentiable point. So those non-differentiable points we've also discussed can be critical values, can be maxes and mins. So we have to include that on our number line. So our f prime number line, putting a 0 on here, we would want to test numbers like maybe -1 or +1. And in this case, the sign is going to change because this is to the 1/3 power. That's a cube root, so we have to be a little careful when we plug stuff in. But when we do, we get a positive here and we get a negative here. So our derivative is positive. This guy here is positive anytime we put a number that's less than 0 in. And this guy here is negative anytime we put a number that's bigger than 0 in. So our interval of increase would be -infinity to 0, and looks like we'd be decreasing from 0 to +infinity. Now, do we have any extreme values? Do we have a relative max or a relative min, or nothing, like in the last problem? Well, remember, because of the domain, this is a point on the graph. And feel free to mark it if we need to. I marked it up top, but let's call it NDP down here. NDP is important to understand. It's a point on the graph. It exists. It's just a non-differentiable point. So yes, we do have a relative maximum at 0, f of 0. Since we changed from increasing to decreasing at 0, increasing to decreasing, we would have that maximum value at 0, and then to find the y coordinate, we go back into the original function f of 0. Okay? So again, guys, really important to understand those critical values are more than just taking the derivative, setting it equal to 0. That's always the step we want to start with, but there's many other things that can be going on that we need to take into consideration. So always identify that domain, always go nice and slow, be real careful with your number line, be real careful with where you're plugging numbers in, and then you'll be able to get those intervals of increase, decrease, and relative maxes and min off the first derivative test.